Ladies and gentlemen, we're going to look at mechanisms in chapter 16. I've tried to group some similar mechanisms. We already learned that this here is called an organolithium. That is chapter 15. We learned that organolithiums react with aldehydes and ketones in the same way that Grignards react with aldehydes, ketones, and epoxides. And we also learned that acetylides in chapter 7 are nucleophiles. That's the first exposure you had then. And here the nucleophile is doing the same as an organolithium or a Grignard would. And this one is called sodium borohydride. I'd like to point out that in chapter 6, it had a different role. It was used to get rid of mercury in chapter 6, the same chemical. As is in life, same chemicals do different things in different environments. So now we got to learn there's a second thing that sodium borohydride does, and this one is when it's reacting with an aldehyde or a ketone. Okay. So organolithiums and Grignards, you always do the same thing first. You cross off the spectator, put the lone pair on the nucleophile, and make sure you identify the charge. It's an anion. Same thing here, except the spectator has two things in it. BRMG is plus. So the carbon with the lone pair is minus. Sodium borohydride. Usually on tests, I have it drawn for you this way, and it was my intention to do this, but I forgot this morning. I usually draw it like this for you. Yeah, because it really hints at what you need to do first. Its name and that picture are a big hint at what you need to do first. Cross off the spectator. And since we're there and we're talking about what to do first there, the end of the name is hydride. What species end with ide? Anions. I need the anion of hydrogen. That's what it says, hydride. Yeah, well, how do we make H minus? Because that's your first step in the mechanism. We need to make H with a lone pair, correct? How does your mechanism make that happen? Just based on knowledge of mechanisms. I need a hydrogen with a lone pair. I have now a hydrogen with a bond. Take both electrons from the bond and put them on H as a lone pair. There you go. Put both electrons from that bond on H, because H is more electronegative than B anyway. 2.1 versus 2.0. Yeah, it's properly named because it's got the more electronegative anion. And this is what it's going to look like. Yeah, a lot of people are saying hydrogen. I've never seen it do that before. Why? Because they've never seen hydrogen do this before. It's H minus. Boron would have an octet violation if it had a lone pair. So don't put a lone pair on B, please. It does, no, it's not there. Boron with 4 bonds shares 8 electrons. Boron on the periodic table owns 3. Boron with 4 bonds has 1 more electron and a formal charge of -1. No lone pair. H minus is a nucleophile. The nucleophile is drawn for every reaction on the page, and it disappeared for dramatic effect. No, it wasn't actually. Lone pair, anion. Watch me do the same thing 4 times. Well, 3.5 times. Lone pair attacks the carbonyl because the carbonyl is very positive. Pi breaks, becomes lone pair on the O. Lone pair attacks the carbon of the carbonyl because it's very positive. Pi breaks, becomes lone pair on the O. Lone pair attacks the carbon in the carbonyl because it's very positive, and the pi bond breaks and becomes a lone pair on the oxygen. Don't have a carbonyl in the next one. What are we going to attack instead? The less hindered carbon, because that's what strong nucleophiles do with epoxide. Yes, that's an epoxide. Whole different ball game, right? No pi. But it has strain. That's the driving force. It doesn't like being strained. Angle and torsional. Bad news. So all four of these reactions are, well, three of them are very exciting. One of them is not very exciting. Why does he say that? Well, you know, one man's excitement is another man's dullness. And it depends on the man, right? Or the woman. You were talking to a synthetic organic chemist here. This guy. What's exciting to them? The only thing that's exciting to a synthetic organic chemist in reality. Making new carbon-carbon bonds. 3 out of 4 cases here, right? So we call that synthesis. So the 3 of these are synthesis. One's called a reduction. But it's the same mechanism. Talk, talk, talk. Here we go. Draw, draw. Every one is going to be an O minus, right? If I drew this in quick enough succession, it might let me copy paste it. And it won't because it's on top of something. All right, just draw the same thing like the students have to. Even this one. I know I haven't finished any of the products except this one. There's stuff missing on the other ones. I know that. And this one's different too. And you keep this bond, you keep this bond. But the exciting stuff is here. Well, that's not exciting when it's an H. We got a new bond here and a new bond here. And isopropyls for this one, isopropyl in blue. And we got the H down there. Now isopropyl. No, it's an acetylide. Yeah, that's nice. And then we got isopropyl. So new carbon-carbon bonds. Think about that. This is a nice way to make them. Hey, if you need a ketone to be an alcohol, this is a nice way to do it. And I just want to remind you why that's called. Anybody remember what I called it just a couple minutes ago? Reduction. Yeah, it's a reduction. And the reason for that is the 2 new atoms are both H. 2 new H's, right? So each carbon replaced a bond to oxygen. Well, the carbon, sorry, replaced a bond to oxygen with a less electronegative H. Electrons got closer to carbon. The oxygen replaced a bond to carbon with a less electronegative H. So looks also like a reduction, but it really didn't cross over any line. It was a partially negative oxygen, it still is, so only the carbon got reduced. But putting H's on a molecule, just H's, is generally reduction. You called it hydrogenation back in the day. You remember that? We got to review that. You know why? Because it's also valid here. It's like a quiz extra here. There's your carbonyl. If it was chapter 6, you could do something like this. Chapter 6 used H2 and PT. And you got 2 pi bonds. They're going to both react, right? Yeah. H, 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 H. So you think you can do the same thing here, H2PT, and you're right and wrong. You didn't do the same thing. You did part of it the same. This ended up being a pretty good review, this or new thing. So what's your take-home message? Only works on alkenes and alkynes. Ketones can only be reduced with H2, PT, if there is pressure. Oh. So this is like an aside, that's something you need to know. So if you wanted to finish the job, you could use H2 and PT, but without pressure, you got this. With pressure, here's good, this nice little picture of review. H2 PT, and you go to the bank machine, you get $5 right there, $5 from the ATM. And you've got your reduction here. Oh, that's not the ATM. That is, what does ATM stand for there? Atmospheres. All right, we got some lab chemists in here. How could you easily do that reaction? With, if you had a syringe and a source of hydrogen, gas, and your chemicals that you need. Platinum catalyst, what would you do? Yeah, I put my chemicals in my syringe to seal it, put a stopper on it. Chemicals in there. Get my tank of hydrogen, fill it, just keep adding hydrogen. You can't see it, so you just make sure. You hear it, and then as soon as you know this, hydrogen is leaving now, put the plunger on, right? And if you got a machine that measures how hard you're pushing, you can actually, force times area is the pressure. It's a thing. And you can get 5 atmospheres pressure just by pushing the right firmness. And yeah, and that's called a par hydrogenation apparatus. Give or take. That one's made of metal, it's not a syringe. It's like a syringe extended to be a vessel. But the idea is the same. You create a piston and make pressure. TMI for a lecture course, but it was cool. So if you want to this is good stuff. If you want to reduce only the ketone, this is the way down here, isn't it? And let's just finish this mechanism because it's the same end for every one of them, this time without exception. They all need to pick up a proton, and I think I can see the proton for everyone on the screen right now. It's HCl, isn't it? I know it's kind of hidden on the screen here, but that's O- grabbing H from HCl. And O- is grabbing H from HCl here. That's what kind of reaction is that? It's a very standard reaction. Acid, base. We are pros with acid base. I'm going to try to lift it just a hair here. You have to write acid base down? Absolutely not. Have to do the mechanisms? Absolutely. I got a new H on an O, and you got to show me how it happened. Every one of those is an alcohol when you're done, right? None of them was an alcohol until now. They were the conjugate base. So I don't need the aside stuff up here. It is useful. I would definitely look at it while studying. And there's the whole picture. And there you go.